Alright, so taking a look at this one. Today we'll be talking about polynomial models in the real world, which follows the same policy as what quadratic models did. Okay, so for quadratic models, we needed 3 points for a degree of 2 function. In other words, a quadratic. Okay. Now, if we wanted to take a look at this and then match it with the n plus 1 principle, for any set of n plus 1 points, so that would be 3, okay, in the coordinate plane that pass a vertical line test, there's a unique polynomial of degree at most n, which is this, 2, that fits the points perfectly. So in other words, if I wanted to do, if I needed 2 points, and if you think about this, this is just of one function. This is a linear function. Okay? Linear models actually need 2 points for a degree of one function. So any polynomial, so for example a cubic model, they need 4 points for a degree of 3 function. Okay? And so on and so on. So if we keep going higher, so this would be a quartic model. You need 5 points for a degree of 4 function. Okay, and then so on and so on. So in other words, we're still going to be using the same model. Now here's the thing though, is that you're just going to be adding letters to the end. So for example, when we are working with, go ahead and get the scribble going. Okay, when we're working with this function, our model actually needed to be y equals mx plus b. So we've used that for a while. But let's say we get rid of m and put an a. So that was ax plus b. Okay. Then we go to the quadratic model, and we needed y equals ax squared plus bx plus c. And that's what we needed in the last chapter. Okay. Now if we take a look at this one, this one would be y equals ax cubed plus bx squared plus cx plus d. So we're just going to keep adding letters as we go. Okay? Oops. Let's widen this a little bit so we can see that d right there. There we go. Okay? And then the quartic, or the quartic, is we are going to be going up to the little bit higher one. So y equals ax to the 4th plus bx cubed plus cx squared plus dx plus e. Okay, so it all depends upon which type of model you're using. Now this one right here, you are going to need just one equation. It just is pretty simple. This one, well, shoot, you would actually need 2, so you need 2 equations. This one we wouldn't worry about solving it any other way than just the way it is. Okay, so let's just go ahead and get rid of that bad boy. There we go. Okay. This one right here, you would actually need, you needed 3 equations because you had 3 variables you needed to find. Okay. All right. This one you would need 4 equations. Oh, that's just ugly. Move that. There we go. As you can see, I'm still trying to get used to this whole new system of drawing on something different. Okay, so that one needs 3. This one would need 4 equations, and then this one would need 5. Okay, and my recommendation is to solve these matrices, or solve these by matrices. Okay, solve these by matrices. You're going to need some big matrices to just work with this. So make sure you are going to www.metacalculator.com and go to the matrix calculator. Okay. All right, and once you get there, you remember the steps for solving a 3x3 matrix of this type of stuff. This one will actually help you out. And the numbers you are going to get are going to be a descending order, A, B, C, D, E, however many you go. But this method is actually something we've practiced quite a bit before, and all you need is just an extra function now when you're working with it, okay? All right, but that's it for modeling polynomial equations. Oh, nope. That is not it, because I forgot to tell you. Make sure when your matrix calculator, you're taking the inverse of the coefficient matrix, and then you're timesing that by the answer matrix to get the variable matrix, or the 3 letters you need. Okay, if you do that, you should be fine when doing this stuff. Okay, all right, that's it for polynomial models in the real world. Good luck, you guys, and just remember, follow the n+1 point principle. Thank you. Bye.